Okay, this is Brian Tebow with my second attempt at trying to get this thing under 5 minutes. So here we go. I'm in the main class. This is kind of how I start up my easy, medium, and hard puzzles. I read them in it from a configuration file as a string. And here is where I can just drop in my different algorithm. I know it's not very slick to have to recompile this every time, but I was kind of running short on time. So if I hit go down here, there I'm done already. I've ran my breadth first search, and you can see the easy results. The output is for my written report and the solution path as described. Okay, so what we do is we basically kick off a new puzzle state. Puzzle state is modeled as a 2D array. So it reads in the string the number of rows and columns that you want. It takes that string and puts it into 2D array. Also down here you have your move right, move left, move up, and move down functions that apply to moving these pieces around the puzzle. So all that gets fed into from the main class. You create a puzzle state, and then you create a node. The node encapsulates the puzzle state, the moves made, the path cost, the depth, all that bookkeeping kind of stuff. Has a compare to function down here for our priority queue, which comes into play later. So from the main function again, now you have your puzzle state, which is put inside the node. You feed everything to this puzzle runner. Puzzle runner essentially kicks off the algorithm, says algorithm.run, and feeds it the root node, and then it just kind of spits out the results, and then it goes back through the list of moves made, and it basically outputs this output that you prescribed in the assignment. So let's walk through an algorithm. So here you can see all these different algorithms. We can walk through depth first search. So essentially we're going to use a stack, and for depth first search, the only thing that changes between these algorithms obviously is the data structure underneath, and maybe a couple things here and there. So I kind of copied and pasted these. If I had more time, I would have done it a little slicker, but I know Professor Radha Jagadisan would kill me for copying and pasting, but here you have it. So basically, while the stack is not empty, you're going to keep popping nodes, and after you've popped it, you've tested to see if you've won the contest. If not, you keep going, and then you check. So this is the important part. You check if it has not been explored yet. Then you're going to add it to your explored set, which is a hash set. It's a hash set because it's you don't need duplicates, so a set doesn't keep duplicates. So now I get my successors according to the successor function. The successor function basically copies the puzzle 4 times. For each puzzle copy, it's going to move it down, up, right, and left, and then wrap that puzzle in a new node, append the move made to it, add 1 to the depth, and total up the cost, and there you have all your puzzles. So once you get through your children nodes, which are your successors, you see if they're in the explored state. For depth first search, I actually did a limit here because it was just kind of running forever. And then you add it to the stack, you keep going. Okay, so let's check our time. 4 minutes and 33 seconds. So you can go through here and see kind of the difference in all these Some we use priority queues. I did want to mention real quick my A*3 algorithm. What I did was, instead of the Manhattan distance, I took the straight line as the crow fly distance as the hypotenuse of the triangle. That's it for today, folks. Thanks.